Now, we're dealing with incomplete dominance. Sometimes alleles show incomplete dominance, in which a heterozygous phenotype, remember that's two different alleles, is somewhere between the two homozygous, the two same allele phenotypes, resulting in a blended or intermediate phenotype. So kind of like a mix of the two homozygous phenotypes. So now we're going to solve some incomplete dominance problems. So in Japanese 4 o'clock plants, red color is going to be designated by the allele big R, and that's incompletely dominant over white flowers, which we're going to call little r. It's not recessive. I know it's lowercase. It's not recessive. They're incompletely dominant. I just picked an allele, little r. And the heterozygous, big R, little r, two different alleles, results in plants with pink flowers. For each of the following parents, we're going to create a Punnett square and record the phenotypic and genotypic ratios of their offspring. So red plants, we know, are going to be R, R. White plants are going to be little r, and we're going to get all of that. Sorry if this is tedious. So all of them are the pink phenotype. So that's 100% or 1 to 0. Easy peasy. Now we're going to cross a red plant with a pink plant. So here we have the red plant right here, big R, and the pink plant right here, big R, little r. I already filled in the Punnett square for you. So we have these two are red, they're RR, so we have 2, and these two are big R, little r, which we know is the pink genotype, so that's 2. 2 to 2, or 1 to 1, or 50%. That's a terrible 0 there. But there's no white. There's no white. Easy peasy. Now we move on to white plant crossed with pink plant. So here we have our white genotype, here we have our pink genotype, and here's what they have. These two, the heterozygous with two different alleles, are pink. So that's 2. These two with the homozygous alleles, two of the same, are going to be white. So that's 2. Again, this is a 1-to-1 ratio, 50-50, no red. And now we have two pink plants mating. So these pink plants are heterozygous. They have two different alleles, and they result in a red, 1 red, 2 pink, 2, and 1 white. So that's a 1 to 2 to 1, or 25%, 50%, 25%. And last question about incomplete dominance. In incomplete dominance, the phenotypic and genotypic ratios are equal. So looking at our 4 o'clock plants, the genotypic ratio, looking at the alleles, are 1 to 2 to 1. And the phenotypic ratio, looking at what the trait actually is, like the physical characteristic, which is white, pink, and red, are also 1 to 2 to 1. So for incomplete dominance, it's true. The phenotypic and genotypic ratios are equal. They're all equal. And that's because the heterozygous, the big R, little r, actually has its own phenotype. It's pink. That's the only reason. In regular inheritance, that's not the case. Now we progress to codominance. Sometimes both alleles of a gene are expressed completely and fully. Neither allele is dominant nor recessive. Instead, an intermediate phenotype, both traits are expressed. ABO blood type an example. Because blood types come from 3 different alleles, it is considered to be a multiple allele trait. The 3 different alleles are A, B, and little I, 3 alleles. Now we're going to list all the possible genotypes for each blood type. Type O is little I. It's recessive. It's also hidden. So if we have A, which is IA, that little I is not expressed, still type A. Or you could have IA. Like with type A, type B can be either IBI or IBIB. Type AB, however, type AB will only be type A, IA, IB. That's it. A man with AB blood marries a woman with AB blood. So we know their genotype, IA, IB. Both of them have that genotype. What are the ratios of blood types of their children? Well, I filled in the Punnett square. For IAIB, for the AB blood type, we have 2. For the A blood type, we have 1. For the B blood type, we have 1. Again, 1 to 2 to 1. No typo. And a man with type O blood, which is I, marries a woman with type AB blood, which is IA, IB. And they have 2 children. The son is type A, AI, or AA, we don't know. And the daughter is type O, II. Are any of the children adopted? Well, we can go to our nifty little Punnett square and figure it out. Oh, look, it's magic. I filled in the Punnett square. So here we see IAI, IBI, IAI, IBI. So only blood types shown are type A and type B. Well, the son is type A, so he's not adopted, so he could be one of these. But the daughter is type O, I don't see any of that. And since there's no type II, the daughter is adopted. So now we're looking at people with type O. Type O blood is II. Parents are going to be II. Only one genotype, only one phenotype, 100% II, type O blood, 3 children, 3 type O's. Fortunately, that's a universal donor, so that's great. They can give blood.